So okay, let's start with lecture 2. So I hope you are very much clear with the introduction of wireless power transmission and various research areas that we have discussed. So as I already said you that the research area which I am going to target, because the motivation has given that uh, uh, for my presentation on mitigation of lateral misalignment problem in wireless power transmission. So in this particular lecture we will only study that is literature survey pertinent to misalignment problems, mitigation of misalignment problems in wireless power transmission system, and also the objective of the proposed research work. So let's start with one by one. So planar transmitter distributed coil antennas. So these are certain some of the literature works where the researchers target to mitigate the lateral misalignment problem by actually designing the transmitter coil antennas, planar transmitter coil antennas. As we can see in figure 15 P1, P1 represents paper 1 over here. So it is a planar multiple anti-parallel square transmitter coil antenna. So what these researchers in this particular design has done is, you can see here winding 1, winding 2, right here in the left side, and winding 3 and winding 4. So there are 4 different types of windings. They have done the current distribution in winding 1, the outermost cluster you can see over here is clockwise, then winding 2 is anti-clockwise, winding 3 is anti-clockwise, and winding 4 is again clockwise. So in this way they have wounded the turns and they have tried to achieve the uniform magnetic field. So how they have done? They haven't done any mathematical optimization or anything. Rather they have mainly focused on simulator based optimization. So after seeing the paper, after regenerating the results of figure 15 P1, what we understood is whatever uniformity has achieved using this paper P1 is very less. Although they are trying to form uniform magnetic field, but the uniformity factor, I just say, I don't want to mention uniformity factor over here, but if we understand the mitigation of lateral misalignment using P1 is very less. The reason is there is no mathematical optimization in this. It is done using a simulator. Intuitively they have wounded the turns on those locations and they have done. So if they would have done using a mathematical optimization using a computational software, then it would have given much better results. That's what we have understood. And the second problem in figure 15 P1 is the design is compromising in quality factor drastically. Whereas figure 15 P2, you can see over here, there is an outer coil and there is a central coil. There are 2 coils. All the coils are having this current circulation in the same direction. But because they have put a central coil over here, a distribution of turns in the central coil, which is also known as auxiliary winding. So because of this auxiliary winding, they wanted to achieve a uniformity in magnetic field. But the problem with this is the uniformity they are achieving only at 1 centimeter, whereas at 50 millimeter or 5 centimeter, the uniformity is drastically reducing in figure 15 P2. That is paper P2. Similarly, in figure 16, some researchers in P3 have tried to achieve uniformity by connecting the windings in parallel direction. You can see in the violet turns, all the violet turns have been parallelly connected. Again, they are seriously connected with the blue turns. Each blue turn is again parallelly connected. So what happens is the current in this violet turns will be, let us say, I1. Then current in this blue turns would be I2. And whereas in the black turn, which is the outermost turn, will be I3. So because of different currents flowing in these turns, you can control the flux or the field formation of the receiver coil. So in this way they have tried to achieve the better uniformity in this P3. But what we understood from this figure, whatever results they have generated in P3, that is paper 3, is that uniformity possesses a tremendous amount of fluctuations. Whereas in figure 16 P4, what they have done is, you can see in the outermost turn, the turns at the outermost turns of the coil, you can see the gap between the turns is very less. The moment you are moving towards the innermost turn, the gap is increasing. So they are actually controlling the spacing between the turns and trying to achieve the uniformity in magnetic field. And figure 16 P5 is similar to what we have discussed in P1, so I am not going in detail. Now the previous all literature is based on single coil distributed turn coil antenna, whereas in figure 18 right now what we are going to discuss is planar transmitter array coil antenna. So you can see in P6, in the figure A, P6 figure A, there are circular coil arrays. So there are array of coils. So coil 1, coil 2 and coil 3. So they have proposed array of coils is better than exciting a single elliptical coil antenna. So rather than using a single coil, you use array of coils. So it will give you a better results is what they are actually claiming. So in this way you can increase the uniformity of the field distribution, as well as you can mitigate the lateral misalignment in greater sense. Whereas in figure 18, you can see the hexagonal coils, the red one and the blue one and the green one are at the different layers of the PCB material. You can see in figure 18 over here. So this is layer 1, this is layer 2 and this is layer 3. So all the three layers are at different distances. You can also see in over here, the blue one is at the top, the green one is at the bottom, that is after 1.6 at the bottom side of the PCB1, and the red one is at the second PCB structure at the top layer of that. So in this way they have connected the three layers, and these three layers are connected in such a way that if the load, here the load is a rat which has a receiving coil antenna. So wherever the rat moves, according to the position of the rat, that particular substrate will power the magnetic field strength to the receiver coil. So this is also array of coils. You can see there are a lot of arrays in this. So in figure 19 P8, you can see so many relay coil, not relay coils, sorry, array of circular coils and a single receiver coil. Figure 19 P9 also, you can see this is called DD coil structure. So you have again 4 coils over here, 4 transmitting coils. And figure P10, the paper 10 is a patent one, and this also have a circular coils. Now we will move on to the transmitter coil integrated with the switches. So here you can see module A, module B and module C and module D. There are 4 modules in the experimental section. So when the receiver coil over here, if it lands on A, let us suppose, then only module A will be activated using a switching circuit and a detection system. So when it lands on B, then only module B will be activated. In this way, they are not only mitigating the misalignment problem, but they are also controlling the flux. But you can see the size of this particular transmitter coil is very large compared to the receiver coil antenna. That is one of the disadvantage. And also what we have understood is the misalignment tolerance is also very less. It can be drastically improved. Then these are the 3D structures. So figure 23, P12, P13 and P14, all the 3 structures you can see. If you see P12, it is L-shaped transmitter coil. And if you see P13, it is a bowl-shaped transmitter coil, inverted bowl-shaped transmitter coil. And P14, you can see it is a tilted one. The 2 sides are tilted at the transmitter coil antenna. So all the 3 are actually trying to mitigate the misalignment problems at the receiver coil antenna using a 3D transmitter coil structures. So figure 24 denotes 3D receiver coil antennas. You can see these are the parallel winding antenna, and this is an orthogonal antenna. This is called T-shaped receiver coil antenna, which is P15. And whereas in figure 24 P16, it is called orthogonally tilted receiver coil antenna. So similarly, P17 was also it is a circular coils instead of square coils in P16. So using these coils, what they are doing is they are harvesting both horizontal and vertical magnetic fields. But the problem with P15 and P16 is they can only capture either HX, HZ or HY, HZ. They can't capture all the three component of magnetic field strengths. So that is the major disadvantage in these receiving coil antennas. Not only that, they also encounter huge fluctuations as the receiver coil misaligns from its intended position. Now we have discussed so many literature designs, right? But how to gauge which one is better and which one is not? So for that, what we have defined is, we have defined something called uniformity factor. You can see over here, uniformity factor of any parameter. It can be mutual inductance M, or induced voltage V, or it can be magnetic field strength H, or it can be power, output power P. Now let us suppose I have taken a design as an exemplary, you can say figure 17C. So this is the transmitter coil I have taken, let us suppose, for an example, whose maximum dimension is 200 millimeter by 200 millimeter. And what I have done is, using the MATLAB, I have plotted the 2D plot in figure 17A and also the 3D plot in figure 17B. Okay. Now what I will do is, let us suppose, let us take figure 17A, which is the 2D plot. The 2D plot is across x is equal to 0, y is equal to 0, which denotes this line. So the line which I am cutting in the 3D plot. So that plot has been drawn over here. Okay. So now what I am doing is, we know that under perfectly aligned condition, the field strength, the mutual inductance. So here I have plotted as mutual inductance in henries. So this is maximum at when the receiver coil is perfectly aligned with the transmitter coil, that is delta x is equal to 0. So delta x represents the misalignment distance from the intended position of the receiver coil antenna. So when it is 0, that means it is perfectly aligned. So it has maximum strength. So to that maximum strength, what we need to do is, we need to calculate plus minus 1% of it, and we have to add and subtract that values. So the tolerance, what we have taken is, you can only, the values of mutual inductance should be only varied between plus 1% and minus 1% of the perfectly aligned values. So that found to be at, that gives the freedom for this particular design in figure 17A is from minus 22 to plus 20. So from minus 20 to plus 20, my receiver coil can freely rotate, freely move from minus 20 to 20, so that my mutual inductance will be within the range of plus minus 1% of the perfectly aligned receiver coil antenna. So this also can be seen in figure 17B. Figure 17B, you can see the square portion over here. This is 40 millimeter by 40 millimeter. So this entire region, my receiver is free to move. So I am giving the user a misalignment freedom, that you have a freedom to move from minus 20 to plus 20 millimeter, that is minus 2 centimeter to 2 centimeter. You can make this much of error, no problem. Your receiver coil is going to receive same amount of performance when it is perfectly aligned. So that is what we are actually guaranteeing the user. Now, how to calculate the uniformity factor? Because we have different designs, and different designs have different sizes in the transmitter coil. So it is the comparison between the designs will be not ethical if we only compare the uniformity region. So what we have done is, we have defined something called uniformity factor. Here, this is the ratio of area of uniform region of the distribution to the area of the transmitter coil. Now here, area of the uniform region of the distribution, let us suppose, is 40 into 40, which we know. And the area of the transmitter coil is, from the outer dimension you can calculate, that is 200 by 200. So the uniformity is found to be 4%. So I hope you understood. Now let us suppose, if I increase the uniformity by 2 times, let us say it is 80 millimeter by 80 millimeter, and if I increase even my transmitter dimension by 2 times, so that is 400 by 400 millimeter. So it is same thing. So it doesn't mean that I have improved the uniformity, because you're parallelly you're also enhancing the transmitter coil's dimension. But if you keep the dimension 200 by 200 millimeter, and if you enhance the uniformity to 80 by 80 millimeter, then you can claim that your design is improved design. That is, you are actually enhancing the uniformity factor. So this is all about the uniformity factor. Once we understood that this is the what is uniformity factor, how to evaluate the uniformity factor, now we can have a fair comparison with the different references that we have discussed in the previous literature designs. Now if you see, the reference P2 is having a transmitter coil size of 200 by 200 millimeter square, but it is actually mitigating, forming the uniform field only in the 10 millimeter transfer distance, which is very low transfer distance for many applications. And it is having a very low uniform magnetic field intensity region, uniform mutual inductance region, which is only 4.84%. So, the type of this transmitter coil is planar transmitter coil. So, whatever we have discussed. And P1, which is a planar multiple anti-parallel transmitter coil antenna, also has the transmitter coil size as 200 by 200 millimeter square, but the transfer distance is 50 millimeter or 5 centimeter. So, it has a uniformity in mutual inductance region is only 6.25%, which is very low, and it is also a planar transmitter coil structure. Whereas P11, 700 by 700 millimeter square, you have seen that switchable transmitter coil antenna with module A, module B, module C and module D. It is also targeting at 50 millimeter, but it has a uniform mutual inductance region of 31.36%. This enhancement of uniform mutual inductance region is because the transmitter coil size for the P11 is very large. So it is a multi-coil transmitter coil antenna. And P15, P16, the 3D transmitter coils and receiver coils are having so much of fluctuations that right after the misalignment itself, it is moving beyond plus minus 1% tolerance. So that's why we are unable to evaluate the uniformity factor for these designs, P15 and P16. So that's the reason the objective of this research is to create a wireless power charging solution that is immune to misalignment, lateral misalignment problem, to cater the range of medium wireless power transfer applications. So to achieve the above objective, what we have underwent an evolutionary process towards the best design which mitigates the lateral misalignment problem in Wpt system. So this is the end of lecture 2. Now I will go in the next lecture with the various evolutionary processes that we have underwent. So with this, thanks a lot.